Hey guys, welcome to part 4 of chapter 21. I rewound a little bit so that I can remind you of what isomers are. We were talking about isomers. So remember, the definition of an isomer is it's two molecules that have, two or more molecules that have the same molecular formula but different structures. So same molecular formula but different structures. So sort of structural isomers, simple structural isomers, are ones that even just sort of in their two-dimensional form, you can tell that they have different connectivities. But some more subtle types of isomers are what we call stereoisomers. And these are they look identical in 2 dimensions, but if we draw them in 3 dimensions, we recognize that they actually are different. So the first type we said were the cis-trans isomers. Cis means same, meaning the groups are on the same side of a double bond or on the same side of a ring. Those are cis. And if they are trans, then they are on opposite sides of the double bond or sticking out on opposite sides of a ring. Trans means opposite. So that's one type of 3-dimensional isomer. The other type we were talking about are these enantiomers. And enantiomers are mirror images of each other that are not superimposable. And you can have a molecule can have an enantiomer only if it has a carbon that has 4 different things bonded to it. Then that means it will have handedness. It will have a mirror image that's not superimposable. So on this next slide, there's a problem here. Let's look at these and determine whether these are molecules that can exhibit optical isomerism, or in other words, do they have a chiral carbon? Can they have enantiomers? Sometimes there's lots of different ways to phrase a question. All right, so what we're looking for is a carbon that's bonded to 4 different things. So here's the first one. It's got a carbon, and let's see, I'm going to just color code it. So we've got a bromine, that's one thing. The chlorine is a different thing. Hydrogen's a different thing. Oh, but then there's another hydrogen. So that's not 4 different things. That's 3 different things. You see that? Because those 2 hydrogens are the same. All right, so this one is not chiral. That carbon is not chiral. And it does not have optical isomerism. There will not be enantiomers. All right, so let's look at this next one. We've got 2 carbons here. So let's start with this carbon. This carbon is bonded to a bromine and 2 hydrogens, and the 4th thing is this whole group here. This whole group counts as the 4th thing, okay? And I can stop myself right here because, again, we've got 2 hydrogens coming off. So that's only 3 different things, something green, something red, and something yellow. We're color coding it. Those 2 hydrogens are the same. So it's bonded to 4 things, but it's not bonded to 4 different things because 2 of them are the same. Okay, next one. Let's do this carbon here. All right, if we look at this carbon here, it's got a bromine, and it's got this big old cluster of stuff here. And it's got a hydrogen and a hydrogen. That's not 4 different things. Okay, but let's try the other carbon. Maybe the other carbon is chiral. Let's see if this one's chiral. It's got a chlorine, and another chlorine. So it has 2 chlorines, and then it has that hydrogen, and it has this big old thing over here. All right, so those chlorines are the same. So either carbon we look at, either way, not going to have optical isomerism because there's no chiral carbon, no carbon that's bonded to 4 different things. All right, and lastly, we'll try this molecule. Let's start with this carbon. We've got a bromine and a hydrogen and a chlorine and this methyl group, actually, CH3. All right, that is 4 different things. All right, so this is our only winner, chicken dinner. All right, this one is the one that would have optical isomerism, that would have an enantiomer, right-handed and left-handed versions. Okay, so there might be a couple questions in the homework that just ask you to identify whether a carbon is chiral. Is it actually bonded to 4 different things? Okay, so the reason that we said that chirality is important, okay, that handedness is important, is in biological systems. In biology, enzymes have very specific binding sites for chemicals. And so while in chemistry, in a tube, chemicals can't really, the chemical properties of 2 enantiomers is the same, but the biological properties will be very different because each enantiomer might bind a different enzyme. And some examples of this in biology are things like your scent receptors. So you have like thousands of different scent receptors in your nose, and 2 molecules that are enantiomers of each other might have 2 totally different scents. In fact, carvone, I won't draw it for us, but there's left-handed carvone and right-handed carvone. And one of them, I can't remember which is which, smells like spearmint and tastes like spearmint. And the other one smells and tastes like rye bread. Those rye seeds contain the other one. So these are totally different tastes and smells to our senses. We sense them as totally different molecules, but they're just right and left-handed versions of the same molecule. So it's kind of a big deal in biology. Another place where it's a big deal in biology is in pharmaceuticals. So when we synthesize molecules, organic molecules in a lab that have right-handed and left-handed enantiomers, all right, when we synthesize them, we get an equal amount of each, the right-handed and left-handed. So we'll get a 50-50 mix. We call this a racemic mixture. It's a 50-50 mix of the right-handed and left-handed versions of a chiral compound. Now, sometimes this doesn't have any negative consequences. So sometimes with a drug, you might have right-handed and left-handed versions where one of the enantiomers is biologically active and has the effect of the drug, and the other enantiomer has no activity, and so it doesn't have any bad side effects. An example in real life of this is propranolol, which is an antihypertensive given to people with cardiovascular disease. All right, the D, propranolol, or the right-handed version, has no activity, so it does nothing. It's just like filler. The left-handed, the L version, is the one that's biologically active and acts as an antihypertensive. So this is the one that actually has drug activity, but the other one doesn't. It's harmless, and so it's fine. But sometimes one enantiomer has a desired function and the other enantiomer has a negative effect. And that was true of this drug that was given in the 50s and 60s for, it was an anti-nausea medication. So it can induce sleep, but also it can be anti-nausea. And it was given to a lot of pregnant women. Not in the U.S., fun fact for you, it was not approved by the FDA in the U.S., but it was given widely in Europe, in the U.K. and Germany especially. And this drug was called thalidomide, and it happens to be an enantiomeric, so it has a right-handed and left-handed version. And the R, the right-handed version, the R isomer, or R enantiomer, was the one that had the desired effects of anti-nausea and sleep-inducing, but the left-handed version, the S enantiomer, was teratogenic, meaning it caused birth defects. So it messed with limb development of the embryo, and so there's a whole generation of babies that were born with deformed limbs, not fully formed legs or arms or both, and they're collectively known as the thalidomide babies. And there just wasn't enough, there was no research on the drug in pregnant women prior to approving it in those countries, and so they gave it widely to pregnant women, and then they found this whole generation of babies being born with limb defects, and they connected it to the drug, and then they banned it for pregnant women. They actually banned it entirely. But now it's approved again for certain, it's actually a useful cancer therapy but it's not approved for pregnant women because of this known side effect of it being teratogenic. And teratogenic just means it causes defects in embryonic development. So if you're not in process of developing an embryo, it's fine. It doesn't have any activity. But this activity was pretty important to know about before giving to pregnant women. Okay, so that's just a little sort of side note on the relevance of these different types of isomers. They seem so subtle, and in chemistry they are, but in biology they're not. So the last thing we're going to talk about with organic molecules, we focused a lot on the carbons and hydrogens that are the foundations of organic molecules. But on that very first slide, I said that organic chemistry is carbons and hydrogens, and also sometimes oxygen, sulfur, phosphorus, nitrogen also crop up in organic molecules. And so we will find these different patterns of groups containing these elements on different organic molecules, and if they have those same pattern groups, they tend to have these similar properties. So we call these things functional groups. An example of a functional group is an OH. If a hydrocarbon has an OH attached to it, that OH group is called an alcohol. All right, and that OH group has specific chemistry. It likes to do certain chemical reactions in predictable ways. And so all molecules that have an OH or an alcohol group sticking off of it have similar properties. So these are some simple alcohols: methanol, ethanol, propanol. It's just a methane with one of those hydrogens replaced with an OH group, and so on and so forth. And so we call them families because they have similar properties. And, all the members of a family tend to share similar traits or features. So that's why we call them chemical families. All right, another example is an amine group. Amines have nitrogens and hydrogens stuck to them. Okay, and they all have similar. There's a whole bunch of different amines. R, by the way, in organic chemistry, we use that as a placeholder, and it means rest, as in the rest of the molecule. So like this CH3 here, and this here, and this here are all different things, but we could call them collectively just R, the rest of the molecule. So all of these are alcohols because they have some hydrocarbon that's connected to an OH. So that's what R means. It's just a placeholder for the rest of the molecule. So when it comes to these families, these functional groups, we call them functional groups, the family or a functional group. So sort of synonymous terms. All right, this is just a table from the book showing you some of the most common functional groups. And they're just patterns of molecules to recognize. So an alcohol is an OH sticking off of a hydrocarbon. An ether is an oxygen that's sandwiched between two carbons, carbon chains. The rest of the molecule is something, some hydrocarbon. An aldehyde is a carbon that's double bonded to an oxygen and single bonded to a hydrogen. And so on and so forth as we go down the list. They're just patterns to recognize in a molecule. And so here's some examples of some simple alcohol, a simple ether, a simple aldehyde. And so all I want you to learn about this is that there are these different functional groups. You don't have to memorize them because, again, in an online format, you don't memorize anything. Everything is inherently open note. But you should be able to use this table and identify functional groups in a molecule. So, for example, we're going to circle and name the functional groups in each of the following molecules. Anything that's like carbon and hydrogen, that's not a functional group. So we're looking for things that are other. All right, like oxygens, nitrogens, sulfurs, but I think most of the ones on the previous slide were oxygens and nitrogens. So in this first molecule, I've got this oxygen here, all right? And so the pattern that I have here is that I have the R group, okay, that CH3 is just the rest of the molecule. And then we have a carbon bonded to an oxygen and an R group, okay? So if we go back to the previous table, R with a carbon double bonded to an oxygen and another R, that's a ketone. So what we have here is a ketone functional group. Technically, this whole thing, I just rewrote it with those R's. Technically, this whole thing is a ketone. This is the simplest ketone out there. So this is a ketone functional group. And the next one over, we also have a C double bonded to an O that I'm zooming in on. That oxygen is different. All right, all of this here is the rest of the molecule. And so what we have is a functional group that's a C double bonded to an O and single bonded to an R, the rest group, and an H. If I flip back to my table here, that is this representation right here. What we have is an aldehyde. So this part here is the aldehyde functional group. What I circled in red is just the R. That's not a functional group. I'm just showing that that's the R part. In the middle one here, I've got a bunch of CHs that I don't care about, that are not interesting. But ooh, I've got this NH2 over here and an NH2 over here. So these look like they're the same, whatever they are. So we're going to go back to the previous slide and look for a functional group that contains nitrogen. The only one here is down here. All right, so we've got, anytime we have an N, a nitrogen that's bonded to anything, that's an amine. So these here are amines, amine functional groups. Down on the bottom left, we've got an OH here, and we have this over here, this COOH group. I can zone in on them pretty quickly because I know my stuff. The OH is an alcohol, and that COOH group is a carboxylic acid. So this is a carboxylic acid group. It's an organic acid. This hydrogen likes to get lost and fall off or be donated as an H+, hence the acid. That's just a fun fact for you. All right, and this OH group here is an alcohol. All right, when we typically think of alcohol, like alcoholic beverages, we're thinking of ethanol, which is this guy right here. When we drink alcohol, we're drinking a lot of ethanol. You don't want to drink methanol. This stuff is poisonous. Propanolol probably is too. I don't know how readily available it is. Okay, last one here. We've got a bunch of things. We've got an OH over here. I see an oxygen there. We've got a nitrogen here. And we have a COOH group here. That's 3 different functional groups. We need to name them all. If we go back to the previous table, we'll see that the OH is an alcohol, and the NH2, anything with a nitrogen, is an amine. And COOH, this is just another way to draw this group right here. COOH is a carboxylic acid. So I say that finding functional groups and naming functional groups is kind of like if you ever read Highlights magazine and you had the picture and you're like, find this pattern in the picture. Like it's like a really busy picture and you have to find like the slice of pizza or like the book or something that's hiding in that complicated picture. That's what finding functional groups is like. You have a complex organic molecule and you have these pictures on this slide. You have these different pictures of these different patterns, and what you're looking for is these patterns in these molecules and identifying them. So there will be some practice problems in the homework that have you doing something like that, identifying and naming functional groups. We're not going to get into the chemistry of these functional groups, what kind of chemical reactions they're involved in. Right now, I just want you to start learning how to see them, how to zone in on them, identify them, and name them. So that's the end. That's all I have for you guys. So practice the homework, and that's the end of chemistry lectures for this semester.